Let's take a look at the normal distribution as approximation of the binomial distribution. And I'll go over some information here, but mainly I'm trying to show you how to use the R programming language to calculate these. Now, in general, criteria for a binomial probability experiment is probability experiment is binomial if it's false or true. The experiment is performed in independent times. Each repetition is called a trial. Like I flip a coin 20 times. There are two mutually exclusive outcomes, success or failure. And success is nothing good. It's just whatever you're studying. So flipping a coin, it could be heads and tails. Success would be if I get heads, and if I get the tails, that'd be considered a failure. Again, there's no good or bad on that. That's just what you're studying. The probability of success, little p, is the same for each trial. So when I flip a coin, probability I'm going to get heads is 0.5. It's 1/2. Now, for a fixed p, as the number of trials in the binomial experiment increases, the probability distribution of the random variable x becomes more nearly symmetric and bell-shaped. As a rule of thumb, and this is from a different book. I didn't necessarily see it in the book that we're studying out of. So you just have to read the book and see what they indicate for it. But as a rule of thumb, if n times p times 1 minus p is greater than or equal to 10, the probability distribution will be approximately symmetric and bell-shaped. Means if you flip a coin 20 times and you're studying getting heads, p will be 0.5, n will be 20. 20 times 0.5 times 1 minus 0.5. You see if it's greater than or equal to 10. If it is, that means you can do this process. Using the normal distribution to approximate a binomial distribution, again, you verify n times p times 1 minus p is greater than or equal to 10. You calculate mu is equal to n times p, and sigma is equal to the square root of n times p times 1 minus p. Mu is our mean, sigma is our standard deviation. And then you figure, I put corrected x there, cx, equals number of successes, using x minus 0.5 or x plus 0.5. And then you figure your probability. And we're going to do that with some pictures. Now here's just generally how you figure your correction factor. Determine if your wording includes a number, yes or no question. Draw the graph, adding or subtracting 0.5, such that, case 1, if the wording includes a number, your shading will include a number. Case 2, if the wording doesn't include a number, then your shading won't include it. What in the world does that mean? Let's look at some examples. And I'm not going to write all the words out. I'll just kind of write out the cases here. X is greater than 30. Well, I have to think about what this means. X is greater than 30. You have to ask yourself if that includes 30. It doesn't. Greater than means greater than 30. It doesn't include 30. So since the wording doesn't include 30, my shading cannot include 30. So I'm going to add 0.5. It would look like that. If I had drawn it the other way, if this had been a 30 here and I had subtracted 0.5, then shaded to the right, my shading would have included 30. Again, if your wording doesn't include 30, your shading cannot include 30. Let's look at probability x is greater than or equal to 30. Now, greater than means I shade to the right. The question is, do I add or subtract 0.5? Now, my wording, x is greater than or equal to 30. My wording includes 30, which means my shading has to include 30. So I'm going to subtract 0.5. Again, very simple principle. If your wording includes the number, your shading has to include a number. Okay, probability x is less than 30. And let me grab a drink here. Okay, x is less than 30. That does not include 30. So my shading cannot include 30. So I'm going to subtract. It would look like that. Again, if the wording does not include 30, your shading cannot include it. If I had added 0.5, my shading would have included 30. Now this definitely won't cover all the cases, but I think you get the idea after we do them. Probability x is less than or equal to 30. Less than or equal to. My wording includes 30, which means my shading has to include 30. So I'm going to add 0.5. And let's say it's between 20 and 30. Oftentimes they use the word inclusive. It means it includes 20 and 30. But again, these lines underneath here indicates it includes them. Since it includes it, up here in my wording, my shading has to include 20 and 30. So here I'm going to subtract 0.5. And here I'll add 0.5. Because again, if my wording includes those numbers, then my shading has to include those. Kind of a variation of that. Let's say it's between 20 and 30, not including 20 and 30. Since my wording does not include 20 and 30, my shading cannot include it. So here I'm going to add 0.5. And here I'll subtract 0.5. Again, the wording does not include it, so the shading cannot include it. And then one last one. X is equal to 30. Well, this one, my shading has to, since this includes it, my shading has to include it. So on the equal to case, I'm going to subtract 0.5 and add 0.5. Excuse me. Because again, if our wording includes 30, our shading has to include 30. Now that's how you handle the correction factor. And again, it's not my goal to teach you what the correction factor is. The book does a really good job explaining that. If you love doing things by hand, I'm not going to show it by hand, but if you love doing things by hand, this would be the idea. First, you verify the binomial experiment and check to see that n times p times 1 minus p is greater than or equal to 10. Then change your x value or values with 0.5 correction to z-scores using this formula. X minus n times p over the square root of n times p times 1 minus p. N times p is our mean, so that's like x minus mu. And the bottom part is our standard deviation, which is the square root of n times p times 1 minus p. And then look it up in your table based upon a shading to the left, right, or between and figure out what the probability is. So it's not horrible by hand. I'm not going to show it, but if you like the previous video where you saw how to do it by hand, that's how you do it. Here, just to refresh your memory, to find the probability, we use p-norm. And x is always the area of the probability to the left. And so you put in x, comma, mu, comma, sigma. In general, to find our probabilities, we identify n, that's always given. They'll say flip a coin 20 times. Identify p, sometimes you have to calculate that, but oftentimes it's given as a percent. And then use a table on the following slide to determine how to enter the function. Now I'm not going to go and read all those through, and hopefully I got them all correct. This is like version 1. I've never come up with this. So that took me a little bit today, and I think it makes sense. Let me just double check here. Minus, that looks correct. Greater than, does not include it, so 0.5. Okay, and that includes it, so minus. And B would be 0.5 minus. Okay, that looks correct. So let's see how to use it. Okay, And so we'll say 80% of students procrastinate on schoolwork. That didn't include you. That's slackers in other colleges. Suppose 200 students are selected. Use a normal approximation of the binomial of 2. Now, n will be 200. When they give you a percent, they're giving you the p. So that'd be 80% or 0.80 or 0.8. And it says approximate probably exactly 150 procrastinate. So x is equal to 150. Now this was our case where it's exactly a value. And since our wording includes 150, our shading has to include it. So this is a case where I subtract 0.5 and I add 0.5. Not that you don't need to do this, but I'm just showing it so you see the thought process, because my table is not does not include all the possible cases. Okay, so we got that. When I say you don't need to do that, you see that I got this right here. Probability x equal a. It fits this form. So this would be our a. So that tells us in R, we're going to plug it into P norm A plus 0.05, or 0.5, I mean. A is 150 plus 0.5, comma, n times P. So we'll have 200 times 0.8, comma, square root of n times P times 1 minus P. The book shows putting these into separate variables in R, and that'd be fine. So here I'm going to have 200 for n, and then 0.8, and then 1 minus 0.8. Closing parentheses for the P norm, minus P norm A minus 0.5. So 150 minus 0.5. And then 200 times 0.80, still n times P, comma, the square root of n, which is 200, times 0.8, which is our P, times 1 minus 0.8, which is our 1 minus P. Okay, so come over here, and I got P norm of 150 plus 0.5. You could go ahead and do that in your head if you want, or plug it in. 200 times 0.8, and then square root of 200 times 0.8 times 1 minus 0.8. You have to be careful in your parentheses. They have to match. You see, I got 1, 2, 3 beginning parentheses. So I got 3 closing ones there. So that's good. Minus P norm. And this one will be the second line, 150 minus 0.5, comma, 200 times 0.8. I wonder if this will let me put it on a separate line. Square root of 200 times 0.8 times 1 minus 0.8. Let's try that. It might give me an error, but that's okay. This is our first problem. It doesn't give me an error, just gives me 2 separate ones. Okay, well, it's just so long you can't see it. And that gives us that as our answer. Now, instead of doing it that way, because that gets kind of cumbersome typing it all in. Mean is a reserved word, I'm assuming. Mu. Mu is equal to n times p. So I got 200 times 0.8. And sigma must be a reserved word. Sig is equal to square root of 200 times 0.8 times 1 minus 0.8. Now when I do p norm, I'll have my 150 plus 0.5 comma mu comma sigma minus p norm. 150 minus 0.5 mu comma sigma. And if I run that, error, object mu.sigma. Oh, comma. There we go. They should give us the same value, which they do. So you can do that either way. Okay, number 2. Let me clear this off. Okay, 1.11% of citizens cheat on their taxes. Suppose 450 citizens are selected. Use a normal's approximation of binomial to approximate that at least 10 cheat on their taxes. Okay, let's write down what they give us first. N. 450 citizens are selected. So N would be 450. If they give you a percent, they're giving you little p. You have to put it in decimal form, though. That'd be 0.0111. Let me think that through. Okay, 0.0, yeah. I can write better than that. That'd be our p. Now, I could figure my mu. I actually like that. It's a little bit cleaner, I think. But mu is going to be equal to n times p, which is 450 times 0.0111. Our sigma is going to equal square root of n times p times 1 minus p. So that's going to be the square root of n, which is 450, times p. Oops, what am I doing a comma for? Times p, which is 0.0111, times 1 minus p, like that. We'll come back to that. It says approximate probably at least 10. Sometimes the hardest part is figuring out what in the world the wording means. At least 10. If I said I'm going to give you at least $10, means I give you $10, $11, $12, or whatever your unit of measure is in your country. So it includes 10. So when I do my correction factor, I'm going to subtract 0.5. Because again, if my wording includes the number, then my shading has to include the number. Now, if you just recognize at least 10 means x is greater than or equal to 10, you can just look at the table I gave you. X is greater than or equal to would be this case right here. So A would be 10. And that says we want to plug it into this. 1 minus P norm. A minus 0.5. Comma NP comma square root of n times p times 1 minus p. Okay, let's go over to R. And mu is going to equal to n times p, 450. And by the way, you could even make this better, programming-wise, cleaner. 450. P is equal to 0.0111. Mu is going to equal to n times p. Sigma is going to equal the square root of n times p times 1 minus p. Now, if you use the same setup, all you have to do is change your n and p each time. Okay. And we said 1 minus p norm. 1 minus p norm. And then a minus 0.5. What was a? A was 10. 10 minus 0.5, comma, and then mu, comma, sigma. And if I run that, let me just double check everything. Then that'd give us our answer there. I like that. That's cleaner. You know, it gets pretty cumbersome if we write everything out like that. I could even, if I wanted to match the table exactly, I could put my a separate. A is equal to 10. Then down here, I'd have a. And if I look at my table, 1 minus p norm, 1 minus p norm, a minus 0.5, a minus 0.5, n times, well, that's mu, but I guess I could write it out that way. But anyway, just an idea. Whatever you need to make it a little bit easier to wrap your mind around. Okay, so let me clear that off. And we'll look at number 3. "87% of American households have outdoor grills. Suppose 310 households are selected. Use the normal as approximation of the binomial to..." So n is going to be 310. P will be 0.87. And it says use normal as approximation of binomial to approximate the probability that fewer than 260. Now you have to think if fewer than 260 includes 260. It doesn't. So that means I'm going to subtract. Fewer than 260 does not include 260. So that would be what our picture looks like. If I were to write out what it means, x is less than 260, we can just use our table directly. So I come up here. That's this second case right here. So A is going to be 260, right there. And that's this one. So I got P norm A minus 0.5 NP square root of N times P times 1 minus P. Or P norm 260 minus 0.5. And then N times P, so I have 310 times 0.87. Comma, square root of n, which is 310, times 0.87, times 1 minus 0.87. Although I'm going to do it a little bit cleaner. Okay. N is going to equal to 310. P is equal to 0.87. A is equal to 260. Mu is equal to n times p. That's our mean. Sigma, our standard deviation, is equal to square root of n times p times 1 minus p. And we're wanting to plug it into this formula right here. P norm A minus 0.5, comma, mu, comma, sigma. That gives us that. And again, if you like the more concise version of that, you type in p norm a, which was 260 minus 0.5, comma, n times p, 310 times 0.87, comma, square root of 310 times 0.87, I don't screw this up, times 1 minus 0.87. Of course, I can't hardly mess it up because I know it'll get the same answer as the other one. And see, we get our same. So that's up to you. One last one. Yeah, grab a drink here. Okay, so 40% of men have noticeable hair loss by age 35. Suppose 500 men are selected, so N is 500. And P is 40%, so 0.40 or 0.4. Now, if it says between two values, you can assume unless it tells you otherwise that it includes them. So down here it says approximate probability between 100 and 2 of them are having noticeable hair loss. So 100 to 200 of them. Now I said you can assume that it includes those, which means over here I'm going to subtract 0.5. Over here I'm going to add 0.5. If our wording includes those numbers, our shading has to include those numbers. Now you don't need to worry about that. And we'll see why. My table takes care of it for you. And I just put the part on here where it includes those two values. As you saw from that earlier example, you could have a word excludes them. It does not include A and B, but this includes them. So A is going to be our smaller number. This is A. B is going to be our larger number. And this says we're going to plug it into P norm. B plus 0.5, comma, N times P, comma, square root of N times P times 1 minus P, minus P norm of A, and our form says minus 0.5. N times P, square root of N times P times 1 minus P. Now, if I were to plug those in, I got B, which is 200, plus 0.5. N times P, N is 500, times P, which is 0.4, comma, square root of 500 times 0.4 times 1 minus 0.4, minus P norm, A minus, so A is 100, minus 0.5, 500, N times P, 500 times 0.4, comma, square root of 500 times 0.4 times 1 minus 0.4. Now, you don't have to draw the picture if you're using that table. I'm drawing a picture just so you can see how these come about. 200 plus 0.5 is my 200.5. 100 minus 0.5 is my 99.5. So if you were to run across a new problem, they gave you something weird, like that right there, then you could draw the picture yourself and figure out how to do the 0.5 correction. Okay, so let's come over here and put this into R. First, I'll try to do it a little bit cleaner. N is 500. P is 0.40. A is 100. B is 200. Mu is still n times p. Sigma is equal to square root of n times p times 1 minus p. And we want p norm b plus 0.5, comma, n times p mu sigma minus p norm a minus 0.5, I think it was. Yeah. Mu and sigma. Or if I were to write it all out, I'd have 200 plus 0.5, comma, 500 times 0.4, square root, 500 times 0.4 times, I can't see what that, there it is, times 1 minus 0.4 minus p norm 100 minus 0.5, comma, n times p, comma, square root of n times p times 1 minus p. Okay, so let's run that. And we get the same value. So that's how you use the normal as an approximation of the binomial. And this table should, I would guess, it would probably cover 100% of the cases you'd ever see. But this is hard to memorize. Unless you got a fantastic memory, memorizing this would be kind of a challenge. So it's better if you draw the picture and think of the correction factor the way I showed you. Then it doesn't require you memorizing all this. But you can definitely use this table to double check yourself.